Hi, this is John Blyler. I'm the content officer at Extension Media for Chip Design Magazine. I'm in Dublin today at the IEF show, and I have the pleasure of talking with Wally Rhines, the chairman and CEO of Mentor Graphics. Wally, in your keynote, you said a number of interesting things. One was that even though Moore's Law, looks like it's going to go away, it's certainly going to have some issues here, that we don't need to worry because there's another law that's taking its place. Talk a little bit about that.
Well, John, there is another law. I've talked about it some before. It's the learning curve, and it tells us what has to happen to the cost per transistor as we grow unit volume with time. So as shrinking in the XY plane ceases to be the easy way to reduce cost, there are other ways to reduce cost, and the learning curve tells us what that needs to be, and we can figure out how to get there.
The 28 nanometers seems to be the Lexus point or the nexus point here for some things. In other words, that seems to be the point when the benefits that we've enjoyed from Moore's Law for the scaling of the transistor cost, for the cost, steadily going down, that's when it's going to end. And questions of integration or disintegration, I guess. How does that figure into all this?
Well, 28 nanometers is quite significant because we've enjoyed a reduction in the cost per transistor of about 30% per year up through the 28 nanometer node. As we move to 20 nanometers and 14, and we add FinFET, we add double patterning, triple patterning, self-aligned double patterning, we're adding cost faster than we can absorb it. And therefore, it's quite likely that the 28 nanometer foundry transistor you buy will be the lowest cost transistor that you'll ever see again, that from now on, at 20, at 14, at 10, and beyond, you'll pay more per transistor, but you will get benefit. You'll get the ability to shrink, you'll get lower power, you'll get other benefits. But in terms of cost per transistor, it looks like 28 nanometer is the golden node.
So it sounds like we're hosed after 28. What are some things that are coming around that should give us hope?
Well, I talked about a number of those. There are innovations that can occur that will keep us on the learning curve, keep us reducing the cost per transistor as we grow the unit volume, and hopefully we can continue that 70% per year growth in unit volume. Some of the ones I suggested tie to the Internet of Things, simply growing the volume of less aggressive transistors and other ways that we can attack the cost per transistor problem through innovative integration and through memory cells, since memory transistors actually dominate the volume with time. And there are lots of innovative architectural changes that can come in addition to growing semiconductor functionality in the third dimension with more layers or with 3D and stacked die.
Excellent. As always, a pleasure. Thank you, Wally.
Thank you, John. Aaron Gobra.
We all know that good systems engineering, working with multidisciplinary teams and following a methodology is very good. However, in practice, it's not done for a number of reasons. And Wally, you had some interesting perceptions or observations on some of the challenges as to why good systems engineering is in practice. Could you talk about those a bit?
Good system engineering means bringing together diverse technologies into a system solution. By its very nature, the specialists in those technologies are typically in different parts of the organization and build their own barriers and ways of doing things in a company. So it's the challenge of a systems company to get a global optimization despite the fact that you're bringing together people of different cultures and technologies that operate somewhat independently. There's lots of experience on this, but some of the things we highlighted in the previous keynotes included how you get the rewards in the same place that the effort is required. So if, for example, you're measuring your wafer fab manager on average yields, then and you're measuring your product engineering group based on final test yields, where is the motivation for the wafer fab manager to assure that product is eliminated early in the process before it costs you a lot, lowering the wafer fab yields but raising the final test yields? And the answer is organizations figure out ways to get that risk-reward paradigm to work together, but it's never easy. It's a continuous struggle. It's why frequently the structure of the organization is a bigger barrier than the technology itself.